now let's look at some architectures that allow us to do all of these different object detection and segmentation. So faster RCNN, this is a pretty popular model that was proposed a few years ago for object detection. And again, it uses the idea of a backbone network. So in the case of faster CNN, they took a VGG network that was pre-trained on ImageNet and froze it. So they said, OK, this VGG network will just serve as an extractor of features. And they then trained an additional region proposal network, which would suggest candidate bounding boxes of specific objects in an image. So they take their feature maps, and this separate network learns to say, well, I think that there are boxes of interest here, 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 and here. And then we can classify what's in these boxes and backpropagate that and train this region proposal network to become better and better at suggesting these candidate bounding boxes. And it turns out that this approach works really well. So I really recommend going to read this faster RCNN paper. It was in a series of papers that led up to this faster RCNN paper. And again, this is a pretty good model for object detection. Following faster RCNN came another paper called mask RCNN. So we saw some examples earlier today of mask RCNN being applied. If you recall, the people walking, and we had the different bounding boxes and segmentation, per pixel segmentation. So that was mask RCNN actually that was used to generate those images. So mask RCNN is very popular for instance segmentation. It's a model that's been around for a while, and there's been all sorts of optimizations and improvements done on mask RCNN since, but it's kind of an important work when it comes to instance segmentation. And so this works by predicting in parallel, so kind of what faster RCNN was doing, the regions of interest, the bounding boxes, but which classes they belong to, but also for these bounding boxes, it has in parallel this series of convolutional layers that then predict a mask. And this mask will determine, again, the segmentation mask for each one of these boxes, what constitutes the object and what constitutes the background. So a very useful, a very neat model with a lot of different tricks to make it work, and I really recommend going to read this paper. UNet is another model. This one is for semantic segmentation. A lot easier to implement than mask RCNN, and some very interesting ideas as well. So it was introduced in the context of biomedical image segmentation, so to figure out where cells can be found in specific slices of, I guess, some kinds of tissue. There was a cell tracking challenge. So what it does is that it finds a way to preserve the higher level convolutions and add them to the lower level features that we get as we go down. So it's called UNet really because the model can be best visualized as this kind of view. So here, as we follow this path down, this is our typical pipeline convolutional neural network that we typically see. So we have our input image, and we do a series of convolutions. So as we go in here, we're doing convolutions. We then downsample, do more convolutions, downsample, more convolutions, etc., until we get to this final representation here. So we get to a volume with which we're satisfied. But then what's really interesting with UNet is then they then do these transpose convolutions to get back up to the original size of the network. But the nice thing is that they have, kind of like in ResNet, these skip connections. So they take these outputs that we had at higher levels, and they combine them back with the features that they combined from the lower levels and are transposing back up. So now you have this mix of information coming from these high-level features closer to the original image, and lower-level features as you went deeper and deeper into your model that you're recombining and restacking together to finally get your output segmentation map. So again, this model works pretty well as well for semantic segmentation, and lots of work was done on top of it to make it better. But one really nice thing about UNet is it's a relatively simple model to implement as compared to, say, mask RCNN, for example, which when you read the paper, you'll see that there are a lot of different tricks to get it to work. SSD, so this is another model I kind of want to mention for object detection. SSD is a model that was, so it's single shot detector is what it stands for. And it was really designed with real-time object detection in mind. It could actually achieve pretty high level performance and still work at pretty high frame rates. And the idea behind the network is kind of interesting. So what they do is that actually they slide well, they predefine the bounding boxes in which objects can be found. So they say, for example, here at each pixel, we're going to fit a series of boxes, and we're going to try to detect, is there an object in this box or not? And they're going to do this at multiple stages in their network. So they're going to do this at the first layer of the network, at the second layer of the network, third layer of the network. And at each layer of the network, they're going to decide whether in the boxes that it's seen, was there an object of interest or not, and classify based on that, and figure out the coordinates of the bounding boxes based on that. And it turns out that this model can work very well. And here you have the comparison of these different models. So faster RCNN, which we saw, and it compared to SSD. And this is on this is on a specific data set, which was, I think, with lower resolution images. And you can see that the performance metric that they evaluated on, so this mean average precision, which we didn't really look at, higher is essentially better. And you can see that SSD, compared to faster RCNN, achieves comparable, if not sometimes better, metrics with much higher frames per second. So again, after these sort of main networks that came out doing object detection, now there was this race as to how can we make these models perform better or just as well while using a lot less resources and being a lot faster. So this brings us also to MobileNet. So MobileNet is a good example of backbone architecture. MobileNet is trained on ImageNet. And so MobileNet was introduced in the context of being able to deploy models to mobile phones in a very cheap way, so to really significantly reduce the number of parameters while not sacrificing on accuracy. And they use this really interesting trick called depthwise separable convolutions. We're not going to get into the details of how that works. If you're interested, the link to the paper is here. I really recommend you read it. So we've seen today how convolution works, and they essentially propose a kind of new or a different way of computing the convolutions on the feature maps to make them a lot cheaper, and show that by doing that, not only could you use a lot less parameters, but you also can get the same or very similar accuracy metrics. So for example, comparing VGG to MobileNet, you can see that you can get very, very similar top 1 and top 5 accuracies on ImageNet, but look at the number of parameters, how they've drastically reduced. And again, this is with time. People try all sorts of different configurations, and eventually, once you find the model that works, you can iterate and iterate on these ideas and try to find better and better and more performant models. So let's look at this video that does model comparison. So here we have different models. So we have faster RCNN, we have SSD. Another model, which I didn't really talk about, but is also a good one for real-time detection, called YOLO. And you can see the difference in object detection. So these are all these trying to compute objects in real time, and you can see all sorts of different stats. It's really interesting because you can see sort of the drawbacks. So for example, you might see how faster RCNN is really stable. There's very little flickering between frames. And what's really important to note here is all of these are trained on a frame. They're evaluated on a frame-by-frame basis. So there's no necessarily temporal coherence in these models. But you'll see that faster RCNN is a lot more robust in terms of changes, whereas maybe models like SSD might be flickering a lot more. So again, this is where faster RCNN might be a lot slower, but might allow you to get a lot more accuracy. So it's really interesting. It's really important to compare these models fairly when you're studying them. Here we have also this very interesting chart. Again, a paper that does a very in-depth comparison to the different models and their different performances. So what we have is we have different feature extractors or backbone networks, so different versions of Inception, and there are even combinations of Inception and ResNet that have been published. So we have ResNet, VGG, MobileNet, Inception. So these are the different backbone architectures that are used. We then have these different meta architectures, so these different backbones used on faster RCNN, and then we have a comparison with SSD. And here we have a very interesting curve where we compare the GPU time, so the time that it takes to compute these features, versus the overall average precision that we get using these different models. So again, a lot of different studies that compare these different models, and it will sort of give you the idea of the drawback between, well, how long does it take for you to do inference, and how much precision could you expect to get from these models? So this is really interesting when you're studying, putting models in production. Is it worth sacrificing accuracy over speed? And sometimes the answer is yes, sometimes the answer is no, but now we have some kind of measure as to how these models actually compare to one another on similar data sets.